Hello and welcome to this Vivado quick take on migrating your design with legacy logic debug IP to Vivado native debug IP using the integrated Vivado logic analyzer. Migrating to Vivado lab tools will enable you to take advantage of key features that are not available in ChipScope Pro. For example, you can take advantage of the new integrated Vivado logic analyzer, which includes scripting capabilities and a common debug interface between the integrating logic analyzer or ILA and the virtual input-output or VIO cores. One of the most requested features was scripting capability. So Xilinx responded, and users can now script the entire debug process, including tickle scripting of runtime controls. Similar to any other design migration, there are a few things you should be aware of. In addition to Vivado ILA 2.1, a new VIO 2.0 core is being introduced starting in Vivado version 2013.1. This means that you are no longer required to use ChipScope Analyzer. As you may already know, the ILA 2.1 core supports both HDL instantiation and netlist insertion flows, whereas VIO 2.0 will only support the HDL instantiation for Vivado 2013.1. Similar to the ILA 2.1 core, as you can see from the table here, we have significantly expanded the debug capability for VIO 2.0 compared to the old version. Let's briefly review the three primary steps that we'll move through in the demonstration. First, I'll show you how to migrate from VIO 1.x to VIO 2.0. Secondly, I'll demonstrate how you can debug your design with ILA and VIO using the Vivado Logic Analyzer. And lastly, I'll point out some design interactions between VIO and ILA cores, and show you how the new VIO core is interfaced with the Vivado Logic Analyzer. On the right, we have a block diagram of a Kintex KC705 DSP targeted reference design. This is what we'll use as the basis for the demonstration. Let's get started. Here's what we know about the design. The HDL instantiation flow is used instead of the netlist insertion flow, and all of the logic debug IP have been instantiated in the top-level design. This includes VIO and ILA IP cores. Remember, with the new VIO 2.0 core, Icon HDL instantiation is no longer required because the tool will automatically detect and connect both the ILA and VIO cores to the debug hub. We'll start off by generating a new VIO 2.0 from the IP catalog and then customize it. For the input side, we need to create 5 probe-in ports to monitor signals from a dual-channel ADC, analog to digital converter, on the external FMC 150 daughter card. On the output side, we need to create 10 probe-out ports to drive a dual-channel digital to analog converter on the external FMC 150 card. We'll also need to provide the initial values on the input side. From here, we can generate the netlist and instantiate the VIO core just like any other IP. Here's the new VIO 2.0 component. Pretty simple, right? So now we're done creating the new VIO 2.0 and modifying the VHDL file. Notice that we added the mark_debug attribute to all of the debug nets connected for both VIO and ILA cores. This is to make sure that these nets won't get renamed or unintentionally optimized away by the synthesis or implementation tools. Okay, we just finished implementing and generating a bit file. Now I'll show you how to use the Vivado Logic Analyzer to debug the DSP reference design that contains both the ILA and VIO cores. We'll start by clicking Open Hardware Session, Open Recent Hardware Target, and select one of the remote targets that I recently connected to. Here are some quick rundowns of the Hardware tab.
XOR is the remote computer that is connected to the KC705 development board. Digilant _ plugin is the USB to JTAG cable that we just opened. Under this JTAG chain, there is the XC7K325T device, which contains 2 hardware debug cores, 1 ILA and 1 VIO. Next, let's program the device by right-clicking the active device and selecting Program Device. Vivado generates a probe file with the .ltx file extension post-synthesis automatically. By default, the tool would generate and store this file at the same location as the bit file. However, if the file is generated manually using tickle commands, the user needs to specify the file name and its location. Just a little bit about the probe file. This file contains probe information such as names, values, trigger conditions, and other parameters of debug nets and cores, most of which can be set at the runtime. This is important because it minimizes the unnecessary recompilation and implementation of the design.
At this point, we're ready to debug the design. Without setting any trigger condition, I will just run the trigger immediately. Here we have the signals that we probed and connected to the ILA core. The 2 signals we are particularly interested in are the 2 baseband analog signals, real and imaginary. We're going to change their format such that we can examine the amplitude value later. To do this, we simply change the waveform style to analog and radix to signed decimal. And while I'm at it, I'll go ahead and change the default color to differentiate between the real and imaginary signals. You can save this waveform configuration and reapply it at a later time to any new waveform. Next, let's take a look at the probes on the VIO core. As I was alluding to earlier, the VIO inputs are used to monitor signals from the ADC circuit, and the VIO outputs are used to write SPI register data to the FMC 150 to adjust the amplitude of the DAC circuit. Notice that the initial values we set on the VIO output probe ports during the VIO core customizations are propagated and powered up correctly. The approximate peak value of the baseband signal is about 24K right now. To dynamically adjust this value in half, we need to write the 77 hex value onto the 32-bit bus register data, toggle the DAC write enable from high to low, and capture the waveform again. As you can see, the amplitude of the baseband signals is reduced accordingly. What you just saw are some of the useful features of the Vivado debug capability. The VIO core on this targeted reference design is also used to calibrate the tab delays for the clock and data lines. For more information, we recommend visiting the Vivado landing page on xilinx.com/Vivado. There you will find links to documentation, user guides, and self-paced tutorials. Thank you for watching, and as always, please check back at xilinx.com/training/Vivado for additional Vivado training.